This video is the first of two videos for finding a limit using a graphical approach. More specifically, this video deals with graphically finding limits when the function is not defined by an equation. In the video, Finding a Limit Using a Numerical Approach, we defined a limit as the following. A limit is the value that a function approaches as the input approaches some value. This definition is for a two-sided limit. There are also one-sided limits that can be defined. Here is the mathematical notation for one-sided limits. The left-hand limit is symbolically denoted by the negative superscript. This denotes the values that are sufficiently close to a and less than a. For left-hand limits, we approach a from the left side of the function. The right-hand limit is symbolically denoted by the positive superscript. This denotes the values that are sufficiently close to a and greater than a. For the right-hand limits, we approach a from the right side of the function. The last thing we need to understand before moving on to an example is the following definition that relates one- and two-sided limits. This definition states that if the left-hand limit and the right-hand limit equal the same value, L, then the two-sided limit will also equal L.
Do you mean that if the one-sided limits as x approaches some number are not the same, then there is no limit? How would that look?
Good questions. The following examples will illustrate this. But first, let's do an example where the left-hand limit equals the right-hand limit. For the function f whose graph is given, state the value of each quantity if it exists. If it does not exist, explain why and label DNE, or does not exist. For part A, we need to find the limit of f of x as x approaches 1. We need to denote where x equals 1 on the graph. Then we can approach this x value from the left and right-hand sides to determine the limit. As we approach 1 from both sides, we approach a y value of 2.
So is this an example where the left-hand limit and the right-hand limit are the same?
Yes, exactly. In this example, we applied the definition that we just learned about the relationship between the one- and two-sided limits. For part B, we need to determine the limit of f of x as x approaches 3 from the left-hand side. First, mark where x equals 3 on the graph. Now, if we approach 3 from the left-hand side, what y value do we approach?
I think we approach a y value of 1.
Yes, that is correct. Now, let's solve part C. What is the limit of f of x as x approaches 3 from the right-hand side?
We approach 4.
Exactly. Now, referring to the definition from earlier for part D, we can determine the two-sided limit from the left and right one-sided limits. The left-hand limit was determined to be 1, and the right-hand limit was determined to be 4. Does this satisfy our definition?
I don't think so, because the one-sided limits did not get the same values.
Yes, since the left and right-handed limits do not equal the same number, we cannot determine the two-sided limit. In the graph, we confirm that the left and right-hand sides do not approach the same value, so the two-sided limit does not exist. So we can write our answer as DNE, which means does not exist. Now, for part E of this example, find f of 3. Why don't you give this a try?
At x equals 3, I see that there are 3 points at y equals 1, 3, and 4. I'm going to guess that the answer is 3 because it looks different than the other 2 points.
Your intuition is correct. The solid circle means that the function is defined at that point, whereas the empty circle means that the function is not defined at that specific point.
Okay, that makes sense. If the solid point was at 3, 4 instead of 3, 3, would this change how we solve the limit?
Great question. No, this would not change the method that we use to solve the limits. Remember, with limits we are concerned about approaching a value. Whether the function is defined at the endpoint or not, the right-hand limit would still approach the same value of 4.